Hey guys, Bill Trombley from Trombley Tool in East Troy, Wisconsin. I'm sure you guys are wondering what in the world's going on today. We had several questions pop up about the use of plastic planishing hammer dies and plastic tooling. And guys want to know how is it that it's working. So I thought I would get a little bit of science stuff, try to keep it pretty simple. So everyone's seen that assembly there. It's called a Newton's cradle, and how the balls articulate back and forth. You know, where are we going with this? Well, we're going to explain a little bit about planishing hammers and power hammers and stuff. A little bit of language that's important to understand before we kind of get started is the difference between compressive stretching. So this is a piece of that clay. If I pinch this, I'm compressively stretching this. The material becomes thinner and it grew bigger in diameter. It's compressive stretching. The other one is elastic stretching. It's a piece of plastic. So if I stretch this elastically, the material is becoming thinner and then increasing in size. So it's the difference between elastic and compressive. So it's just important to get a couple of the words correct so that we can understand what's going on and when we're talking about the sheet metal. If you look at these Newton cradle here, I'll bring you over to this table. Like this. What you're also looking at is my pneumatic planishing hammer as it's disassembled here on the table. So this is my CP machine here. And what we have is the upper body. This is the upper part of the cylinder. This is the outer housing here. And it has this piece that moves back and forth. Some guys go, it's a piston. What it actually is a hammer. So it's a articulates back and forth with air pressure. How this works is the same as how this cradle works, sorta. The cradle works by having gravity pull on the ball. We're taking here and we're using air pressure to move the weight back and forth. So the hammer comes down, it hits the back side of the die, so plastic upper die. The energy then is transferred between the sheet metal into the plastic lower die, into the plastic holder, or into the lower die holder. So how that works is it articulates back and forth and it causes it to hit. So how come when we use the plastic dies we add no shape, but if we use steel and steel dies we add shape? There's several reasons. One of them is, and this is the geek out science portion of it, is this formula here. This is a physics formula that says force equals mass times acceleration. And everyone's going to go, dude, you know, that's pretty advanced. It's pretty simple. So the mass of it is the hammer weight plus the weight of the die when this hits, and then how fast do I throw it. So that's like if you guys are into shooting sports, you know, you can deer hunt with a big, huge, heavy caliber rifle. You could also deer hunt with a very lightweight rifle. You just got to make the bullet go faster. By making it go faster, you get it so that the force at the end is still the same. And that's all this is saying. So if I increase the mass and I slow down the acceleration, it's just as much as if I make the mass very small, but I spool it very fast. Hopefully that makes sense in a simplistic of terms. So what's happening is you have the weight of the hammer plus the weight of the steel die, and that causes the shape to develop. By using this, because this is so much lighter than the steel die, I have less mass. I'm still running it at the same speed, so it hits lighter. To help prove that, CP has a 12-inch floor model CP planishing hammer, and then they got a 24 and a 36. The 24 and the 36 use air motor that's this long. The 12-inch one uses an air motor that's that long. And the hammer in here is actually a smaller diameter hammer, and it's slightly shorter. So the 12-inch motor hits lighter than the 24 or 36 because you're moving it at a shorter distance, it's not accelerating as fast, and it's a lighter weight hammer. So it's much more of a nicer planishing hammer for doing finished plenish work in lightweight aluminum with the smaller motor. And that's how come for my 24-inch CP machine, I actually retrofitted my machine and I can swap out either motor. I can go from the big motor to the small motor to be able to get it so that I can use my big machine to do lightweight plenish work, as an example, right? We know this to be true. Kent White had offered, I think there was 5 different motors in the series that he had for his planishing hammer / pneumatic power hammer. So by making the weight bigger or accelerating it faster, the more force is created, the more efficient it becomes. So that's how that works. So the plastic dies, because they're lighter weight, hit less, and don't create the shape. Another reason why is the steel die and the steel hammer weight inside the planishing hammer and stuff like this. Metal components are crystalline structures, and they're excellent conductors of energy. We know this to be true when it comes to electrical wire. And guys are going to go, there's no, it's not the same thing between electromagnetic force and the force that's being generated here. I understand that, but it's similar. So electrical or crystalline structures, all metals, are excellent conductors of energy. Rubbers, plastics, and wood are lousy conductors of energy. That's why we coat the wire with a rubber jacket, right? It's a lousy conductor of it. So you can go, where are you going with that? Well, I have my ball peen hammer here. This is a snap-on hammer. Has a steel head on one side and a rubber end on the other. So the mass is the same, the amount of energy that's here is the same. If I take this nail and I nail it into wood, it's easier if I hit it with the metal end, and I can still set the nail with this end, but it takes just a little bit more effort. And that's because energy is being absorbed into the rubber head. So that becomes important to understand and to think about. Is to the reason why the plastic is less efficient to cause shape. And in essence, why in the planishing hammer it does not. One of the questions then that popped up was, guys know that for my power hammer, my number 2 Pettingill, I have a plastic upper. And guys are going, so what you're saying is you can never develop shape with plastic tooling? No, that's not true. In the power hammer, I can. But the dies are held in with a die key into the upper hammer weight. There's a lot more mass there. So there too, because I have a lot more mass, I can throw it hard enough where I can actually create the shape with the plastic tooling. So with the plastic tooling and the planishing hammers just happens to be the sweet spot that we get to where we can level out panels without causing it to add shape. So people go, well, in another question that popped up is how come it'll cause the bend to occur and straighten out these lumps and push down the highs and bring up the lows without actually squishing out the material? And this gets into you know, if you're exceeding its yield strength, how come then we have to exceed the yield strength to cause the bend to occur? How come then you're not pushing it apart? It was a question that was posed to me. And the reason why on that would be, as picture this is a piece of sheet metal. It's just a very thick piece of sheet metal, but it's still a piece of sheet metal. And guys go, well, it's a bar stock. And you go, yeah, well, this makes it easier for you to visualize. This was a piece of sheet metal and this was bent, or if I had to bend it, it's very easy for me to bend this material this way, right? To bend this up or down. A lot more than if I were to try to compressive stretch it like this piece of clay by hitting it here and moving the material this way. And the reason why is you got the stiffness of the material itself. So it takes the path of least resistance. So it's easier for the bend to occur by bending it that way than it is to try to take and push this material into itself that way by compressive stretching like we would with steel on steel dies. And even though this is a piece of bar stock, the principle is exactly the same as it is on this piece of sheet metal. It's just the cross section is a lot thinner. So that's why. And then the one other question that was posed was if steel on steel dies cause this shape, and then if you use plastic dies and it doesn't, then using a rubber die would be even better. That it's the surface hardness of the material that's causing whether it shapes or it doesn't, and that it doesn't work that way. That is not true, and here's why. The plastic holds its shape. Is there a little movement in the plastic with each hit? Yeah, you know, there's a little bit that it goes on. But if I went over here to this plastic planishing hammer die, excuse me, this is a steel die. This is a CP die in a holder that I have. It's a steel die. And I have this rubber mallet that I just showed. And I take this and I hit it. You can see the dent occurred. Why? What this is doing and what the rubber is causing is, instead of a compressive stretch, it's an elastic stretch. So the rubber is causing this material to be stretched over the die and elastically stretches the material. So, and that's why you got to be mindful of which materials you use and when and where and how. And I can show this and then we'll be pretty well wrapped up. This is a short video just to help answer the questions. We have over here the the hot dog die and the rubber upper that we used in the last video on doing reverse curves. So this is a hot dog die. This rubber pushes over the top of this and stretched the material. Elastically stretched the material, just like it did with this. And that's how the process works. So you can see here there's a couple ideas to think about, but that's how plastic tooling and why it's beneficial and it works so well. So, and I hope it helps. Have a good day. Bye.